Hello, my name is Daniel Uscanga, and I will present to you my argumentative exam, my first argumentative exam. We have five problems. This is the first one. It asks us to get to this equation having this one. So in order to get rid of the derivative, we just integrate that. We did use substitution. Then we have a normal integral. So we continue, we have our constants, we rename it C3 as 1. We get rid of each logarithm in order with exponential functions. And then in order to get to a lonely, we solve for t. We did another exponential move. So we know exponential to the constant will become just the constant. And then we get to solve for t. We then interpretate as it asks us here. We then interpretate, let me put a timer on this in order to know better the time. Then we make our own interpretation. It depends on t, on 0, the initial condition. In order to have these differences will be time being equals to 0, like there is no movement between cooling or heating down. So then we go to DC, that C, it's basically the differences between the initial and the final, like the temperature we will obtain minus the ambient temperature of the room in order to generate this equilibrium, this thermal equilibrium. Then we have our part 3 in which we got the DC as a DC and K variables, like we discovered them with our data that is shown here. We get a minus C because in this case it is cooling down. If the case was different, we would have gotten a positive one. Then we have our cooling constant, in which we just solve for K. Then we make our mathematical model. I'm sorry, in here it will have a T, like literally of time. I forgot it. It was a handwritten error. Then we have our third problem, in which they ask us to the time it will take to cool down. And we just solve for t our mathematical model. We have it with our own data. In order to get that, it will take 3,251.21 seconds. Then we have the problem 2, in which they ask us to derive an explicit expression for t over time. Here we have our first equation, in which we don't have anything related to time. We have this difference of temperatures, mass, and this is a constant that it's given in the literature of each material. So we just add up 1 over t on both sides just to have the t. We know quantity of heat over time is pressure. So now we have an equation that includes just one variable of time, and we solve for it. No, we solve for the final temperature. As we know, final temperature will become a function of time, because our final temperature will determine us the time it took in order to get to that. Then we have this as a linear equation form, because we know this is our pending or a tangent line. Let me see that. Our slope, it will be our slope, I'm sorry. And we have also our MATLAB model. The MATLAB model of, let me explain very fast, the MATLAB model for 1.4 and 1.5. We just did our procedure. We name our variables, each of them, and then we plot a graph. We did it in 3,500 seconds because we need 3,251. This is the difference between T0 and TA. It's negative um because of the uh because of it is cooling down, yeah. And yes, then we have the rest of the of the problem in correlation with the other one, as it makes a Euler's method comparison. And we know Euler's method is a numerical procedure that is used to solve ordinary equations in a more precise way. We have here our Euler's method graph and our um, other method graph with the cooling constant we got. We did it in steps of one with saving the time in a zeros function to have it with constant updates. And yes, then let me explain back at it again on the problem number two. We did our own MATLAB graph again. We just name our variables with the data that it's shown here, as we should have expect. It is a linear function in which our slope is pressure over mass, and the c, that is the calorimetry constant. And also we know we can get to it with deriving the point. And yes, we have then the problem number three, in which they asks us to get to a final temperature equation. We have this calorimetry principle, this quantity of heat equation. We have one for the water, one for the copper. Then we just did some algebra, some substitutions in order to get to, also factorization in order to get to this equation. The problem 3.2 is just finding the final temperature. Why do this happen? Why does this happen? It is because we have one element that is gaining energy. So we have this water being heated, so the energy will be transferred from the heater to the water. Not all the energy will be transferred. Then we would need to do some Gauss Jordan some Gauss Jordan method in order to get to the final slope to a real one, because some of the energy is transferred to the environment and also to ourselves. Okay, then we have our problem number four, which uh, which states, back at it again, we need to change some equations in order to get to one. Well, we have our bank. As we know, 3 alpha it's beta, I'm sorry, and we have this length formula, which will be then moved as a radius one and height one in order to get to our volume. This formula, it's linear, so then we did it with these two. We did algebra, we solved the binomial, we solved FOIL, we simplified it, And as we get to this part, delta of temperature squared, it's really small with also this, yeah, so it will be like multiplicating alpha times zero, so we can cancel it out. Then we get that this is volume. So we just solve for the delta volume. As we know, this is beta. And on the 4.2, we just got the thermal expansion. The final thermal expansion volume, that is 10, that is this one. But in order to get to the final volume, we just needed the difference in volume. Then we added up in order to get to this equation. This equation tells us that the difference of volumes, it's determined by 3 times uh, this calorimetry constant. No, I'm sorry, this thermal constant 3 times, because it is a volume, and times the difference in time times the first volume in order to get to our difference. We know this is some um, we have a small numbers, so this change is like really a small change. Then we have the problem number 5, in which we have this graph that tells us there is an increase, like by just looking at it, but by the algebraic expression, its explanation is that when pressure and volume increases, we have n and r as constant, so temperature will increase. So yes, if we have this increasing, these are constants, it will increase. If we have this decreasing, and also by looking at this and the arrow, the clue is the arrow, we have that. Then we have this problem in which they ask us for the work done. We know this is a rectangle and a triangle, so regularly we should do this with this, but I did it taking the areas of both of them because I think it's easier. And in this case, it is like really marked on the height and the base, that the base is just the difference between our data and we just did some formulas in order to get the work done. We know the work done for some graph is the integral and also the areas under the curve. So in this case, we took the area under the curve in order to get to solve the problem number 5. This is my final, no, not my final thermodynamic argumentative exam. Hope you enjoy it, and thank you for everything.